All right, folks, welcome back to the SNIA Experts on Data podcast. My name is Eric Wright. I'm the Chief Content Officer at GTM Delta and co-host of this amazing podcast here. So lucky because I'm surrounded by experts on data, experts on so many things, and I've got two fantastic folks joining me today because we're going to talk about what's new in storage. As we're recording this, we're wrapping 2024, which has been a big year for so many things. We've seen a lot of innovation. Show season winds down and the tech events start to move into let's prep for next year. But the one thing that's interesting, of course, is the work that's going on in SNIA is well ahead of stuff you're going to be seeing announcements for in the first part of the year, because the stuff that we're talking about is stuff that really is going to have pretty interesting, long-lasting effects. But really, the thing about it is the people that you get to hang out with and spend time with, learning about what's happening, what's coming, and really the idea that we can innovate at incredible paces when we collect together in great groups like SNIA. So with that, I'm going to open up. And Cam, if you want to do a quick introduction for folks that are brand new to you, and then we'll move on to JM next, and then let's jump in and we're going to talk about what's new in storage for 2025.
Yeah, sure thing. Thanks, Eric. My name is Cameron Brett. I'm co-chair of the SNIA SSD SIG along with Jonmichael, and we try to be an authority and representation for the industry for things about SSDs, such as form factors, classification types of SSDs, TCO models, things like that. So Jonmichael and I work very closely on that. I am also an employee of Kioxia.
And Jonmichael?
Yeah, Jonmichael Hands, Senior Director of Product Planning at FADU. And we thought it'd be fun today to get together and chat about some of the new trends in storage. There's a lot of discussion on, of course, AI and storage workloads, QLC, Gen 6, EDSFF, CXL, all kinds of fun stuff. So we thought we'd just kind of go back and forth and chat about a little bit what's going on in the trends for next year.
Well, there's no better trend than when you can just say, let's rub some AI on it. So Cameron, let's talk about what is AI doing to, drive trends and changes in the storage industry?
Well, I think both Jonmichael and I will have a lot to say about this, but at a very simplistic level, GPUs and DRAM and storage are definitely the big cost drivers for AI. And storage is critical for AI systems in all the various phases. And one of the goals of storage is to help keep the GPUs working so they have less idle time. All types of workloads are being used. Pretty much all the SSD attributes are tested. Low latency, read-write throughput, small block, large block IOPS performance, et cetera, et cetera. In some AI phases, the lowest latency and highest performance are needed, but in many cases, it's not. This is where you have a choice for kind of a cost versus performance metric comparison, and you can choose different SSDs. The highest performance, lowest latency SSDs are enterprise class, and the data center class SSDs still provide very good performance and latency, but have a focus on consistent and predictable performance and latency. So these are typically required by hyperscale applications. And this is one of the pages that Jonmichael and I worked on, kind of having a distinction between enterprise class and data center class NVMe SSDs. SSDs will also likely play a role in the expansion of memory space to augment existing DRAM in places like RAG, specifically with approximate nearest neighbor search, or ANN. Being able to scale by storing both index and vectors in SSDs as the database grows will boost performance while keeping costs in check, since the SSDs can, in some cases, replace DRAM. You'll see more technologies like this in 2025. So there's a lot going on. I'll hand it off to Jonmichael to say a few more words on SSDs and AI.
Yeah, where I started was Meta has, with the Llama 3 training, obviously it's open source model, and there's been a tremendous amount of information they've put in those white papers. And research studies on like the storage configuration for the actual training, which I thought was really fascinating. Like for instance, in the Llama 3 training, there was like, I think it was like 16 or 17,000 GPUs in the cluster that they were actually used for Llama 3 training. And in that they had like, a 240 petabyte NFS cluster, and they're doing this with NVMe over Fabrics. And they kind of describe their tectonic architecture that they used to use for warm storage and blob storage and how they migrated that to flash. But the really interesting part is these ratios, like this checkpointing, where, it's very bursty. They said up to the peak bandwidth of 7 terabytes a second of bandwidth needed to do these checkpoints on the cluster, which is just insane, right? You have to remember all these GPUs have to be coherent to do the training. So I really enjoyed, these videos that Meta put out. There's one, I think it's called Training Llama Storage Perspective. They kind of talk about some of these challenges and tail latency. Obviously all these storage vendors are trying to ask the question of like, okay, what do we do in storage to make it better for AI? For one, I think it's clear that high performance is needed. Like, lots of bandwidth, for like checkpointing and sequential writes, in training for random reads. Like I ran all the MLPerf storage stuff, and it's really just like, the 3 MLPerf workloads that are up for training are like the UNet 3D and ResNet are all just like high block size random read. And, there wasn't, unfortunately, in the Rev 1.0, there wasn't unfortunately that much stuff you could tune on the drive to make it go faster. All the tuning was like file system and, the network storage level to make the training workloads go faster. And so we're actually, I am part of the MLPerf storage work group, and they're targeting the 2.0 for like middle of next year. And there's a bunch of stuff they're trying to tackle: RAG, S3, checkpointing, like updated training benchmarks. So everybody wants to know, like, what can we do to like benchmark the storage for AI. The other really interesting thing that happened was NVIDIA has kicked off this like storage.next motivation, which, unclear if they're going to, there's going to be some, obviously a bunch of storage vendors and companies are part of SNIA. They want to maybe do this in OCP, maybe some stuff in NVMe. They don't really know yet. But I mean, there was 110 storage vendors on this call that the kickoff meeting. And it was really about like, where are we today? And, just that was part of what Cameron and I were just talking about, like, characterizing these workloads, like data loading, sequential versus semi-random, checkpointing, sequential, large block size, RAG, embedding lookup, small block size, semi-random, and understanding some of these workloads. But they're working more in the future. And I think that was really interesting to look at the perspective of, right now it's obviously like, storage is not a huge spend in the CapEx for AI. If you just look at, I think some of these hyperscalers were over $30 billion in a quarter for CapEx, on data center spend. So like, if you just think about, storage as a 2 to 5% or something of these giant numbers, like it's very easy to see why the storage market is so interested in understanding this. But it was really nice because they kind of focused on, okay, where are we at today? We understand these. I just mentioned like some kind of basic understanding of some of these training workloads. You need lots of bandwidth. You need lots of IOPS. But I thought it was really interesting of where they are going and what they were explaining. And I think, CJ gave a session on this at OCP as well as Supercompute. And I think a lot of those sessions are up on the internet. But they were the ones that pioneered this GPU direct storage, and wrote the white papers on big accelerator memory and the GPU direct. And so they're showing us this world where the IOs come from the GPU directly to the SSD, or NVMe or Fabrics through some kind of like Bluefield NIC or something directly to the SSDs. And this looks a lot different than storage today, right? It's thousands of queues, thousands of threads, and the really interesting use case I thought about RAG was, we talked about CXL a little bit, and why they're like, okay, memory doesn't solve, it solves your like couple of terabytes problems, but what if you have a database that's 100 terabytes or 2 petabytes for RAG? Like, it's not going to work for memory, right? You need SSDs. So the thing that just blew my mind was their target for Gen 6 is 200 million IOPS per GPU.
Good golly.
So their challenge to the storage industry is like, how do we get there? Like, it's very clear, even
no pressure.
NAND SSDs, okay, we can get to like 7 million IOPS, Gen 6 with standard, standard SSDs we have today. But like, what are we going to do? So I thought this was just a lot of fun. I mentioned a lot of this work is just getting kicked off, but there's so much going on, right? I mentioned, and I'll just do obviously the shameless plug for SNIA STC. I thought the AI sessions were fantastic. I went to the
100%.
one from D, I went to the one from Dell, and one from Microsoft. They were so good, and most of them way over my head, which means that they're good. That's the STC way.
Yeah, well, they're amazing to watch because of how quickly people sort of head to the stage, and the 1 hour talk is what precedes the 3 hour talk. That really is the one that we move to the hallway track, and there's such a great set of people there that are really sharing what's going on. It's such a beautiful sounding board. And, it's funny, you talk about like, how do we predict what's coming? And that there's so many parameters, so many opportunities for tuning, changing, and then workloads. Like this is a brave new world, although some would say it's a silly new world, but it is brave in what we're trying to accomplish and trying to do it in the most environmentally, intelligent way. We know there are many different sacrifices in this equilibrium of what we have to sacrifice in order to achieve these gains. So it's amazing. So Jonmichael, one of the things you mentioned there was PCIe Gen 6, and obviously we're seeing some neat stuff that's coming around that. So what does the 2025 outlook, as far as coming with Gen 6, and why is this actually important in what we're seeing around some of the innovation coming up?
Yeah, the funny thing is, every single generation there, and Cameron and I have had this discussion with SATA and NVMe. We first came out with NVMe. It was like, why does anybody need 7 times performance? SATA is just fine for these workloads. Like, and then you go from Gen 4 to Gen 5, you double the bandwidth. I don't think people quite understand like that. You're doubling the bandwidth. It's 2x the performance. And right. That's why these interface changes are so important. And, as we just talked about AI, like when you go from, say, 200 gigabit networking to 400 gigabit networking, now you need to go from Gen 4 to Gen 5 on the NIC, and you need to go to Gen 5 on the drives to basically saturate the network and saturate the GPUs and all that stuff. So we are seeing now like all the Gen 5 shipping in volume from all the vendors, which is great. It means, So, we saw a couple announcements for Gen 6 at FMS, just kind of like the companies are working on SSD controllers. I don't expect any of them to ship in 2025. I think there's a lot of engineering work that goes on. But the interesting new, obviously the new company in town for, high-speed, computing is, NVIDIA, and it's clear that, the AMD and Intel, what they've said about, Gen 6 is, it'll be like, 2026, 2027 timeframe, right? Where NVIDIA is like, we have Blackwell and we have DPUs, in Super NIC from Mellanox that are going to be shipping Gen 6 next year. Like, so they're asking for Gen 6 yesterday, right? Like what?
Yeah, we're already, the demand is already there. No market testing required. So
back to that, like, we're going to go through this cycle that we go through every time we go through an interface transition, which is, why do we need the extra performance? And I talked to a few of the hyperscalers about this, and they said, well, if you can do Gen 6 at the same or less cost than Gen 5, then of course we want it.
Of course.
So, and when they say cost, they don't mean like cost of the controller, cost of the NAND. Like that stuff doesn't materially change. It's really the retimers and the system and the low loss material and all the other stuff in this
overall system cost.
Yeah, and when they say TCO and lower cost, like they mean like, okay, how do you go from Gen 5 to Gen 6 without increasing the system cost by 30, 40%? Because that's just not going to work for them. And so, again, every generation we go through this. It's not possible. You have to have extra cost to get there, and then people figure out ways to, retimers are getting more common. There are more vendors. Their prices are going down. So. If it wasn't clear from the AI that AI absolutely needs higher bandwidth drives, They are absolutely going to 800 gig networking, and they need Gen 6 drives, and they have Gen 6 GPUs for Blackwell, and they want Gen 6 drives. So it's really a race. The storage vendors are going to try to figure out how they get there. But
NVIDIA, when NVIDIA wants something, and they're ready for it, people are going to jump as quickly as possible. So NVIDIA is basically the bellwether for AI right now. So
that is definitely Jensen is the new name, drips off the tongues of so many pundits, because we see, like, when there's announcements coming up, I know they've got stuff with CES, so we're likely going to see tons of new announcements coming about what's already on the ground and what is coming, and then this always has this incredible downstream effect. And it's funny that, like you said, JM, this idea that why do we need more? I used to have my network team at one organization, and he'd always tell me, he's like, I say, hey, we need to get on, on the good backbone for this one. He said, we need to move off the 10 gig to the 100 gig. And he would just look at me, in that grisly networking style through his cigarette smoke out in the parking lot, going, if you can max the bandwidth on that thing, I'll buy you lunch every day for the next year. He says, this isn't a bandwidth problem. You cannot possibly stress the bandwidth, because at the time, there's always the bottleneck was way closer to the workload. And now that is just the need to send over the wire is incredible.
I forgot to say one key trend, right? Which is, obviously all the controller vendors are trying to figure out, okay, can we make a controller that's twice as fast at similar power? You have to go to, fancier TSMC nodes and, do lots of tricks, to basically be able to scale the performance. But the NAND also has to get more power efficient. You can't double the bandwidth and double the IOPS and then not have a huge generation over generation improvement in NAND, IOPS per watt and bandwidth per watt. Because if you want to saturate Gen 6, Gen 6 is 28 gigabytes a second, and it's 7 million IOPS, and that's a lot of IO.
And you still have the same power envelope per SSD.
Yes, exactly. So this is incredibly important, as kind of moves us into this discussion about energy efficiency and form factors, and like all this. Gen 6 just highlights all these issues that were kind of present on Gen 5, but not like they were definitely magnified compared to Gen 4. But in Gen 6, they're like very polarizing.
Yeah, we've gone from potential walls we're going to run into to we quite literally have been pounding against these walls now as we close up the year. Now, then on the hardware side, QLC, neat stuff are going there. And it's funny, over the years, I remember we always sort of struggled with which is the enterprise grade, commercial grade, and there's a combination of both software, firmware, three things: software, firmware, and hardware that are giving us gains that allow us to both extend the life cycle, which is better for that sustainability capability. And just in general, we're seeing in-place improvements on existing gear, but then now we're seeing new developments that's happening that's taking these learnings and now baking it into the hardware layer that potentially we can unlock future, efficiencies, again, with better use, better software that can leverage these capabilities. So Cameron, you want to talk about what's going on in QLC and why it may not be the year of VDI, but it will be the year of QLC.
Well, as Jonmichael was commenting on all the improvements in performance, improvements in storage density has to happen at the same time. And, QLC has been talked about for many years. And, this is likely the year when QLC will kind of take a major foothold. There were some QLC SSDs out in 2024, maybe a little bit in 2023, but 2025 is likely when it's going to take a big foothold, especially towards high cap SSDs and, possibly even into some cold or archival SSD use cases. One thing about the storage density, and we'll probably touch on this a little bit more during, talking about maybe power efficiency, is that, I mean, once you grow an SSD in capacity, you still have the same power envelope for an NVMe SSDs. There's some cases where you can kind of go up the power envelope to 40 or 70 watts, but generally speaking, keeping it at 25 watt cap is kind of the mark that you don't want to go over for an NVMe SSDs for an NVMe SSD. Not all QLC is going to be created equally, and they are going to vary by supplier, and a lot of it is going to depend on the chip and packaging architecture. So depending on there's CBA architectures, CUA architectures, and some of those will have an effect on the robustness of the cells, and thereby can determine whether it's really fit for enterprise use or data center class SSDs or archival or relegated to client, type of workloads. But definitely QLC is going to be certainly the key to the high cap SSD space that we're going to see a lot more of in 2025.
I, for one, welcome our high cap QLC overlords.
It's funny, when I talk to a lot of folks about QLC stuff, the more I realize I'm like, oh my God, we have to just go back to the basics. Like, I think that some people forget like some of the absolute NAND fundamentals. Like, so you go from 3 bits per cell to 4 bits per cell, you're storing 33% more capacity, and you have a cost reduction of 25%. Now, like, that's just at the NAND level. And if you have like one wafer, and you can turn it into TLC or QLC, like that's the density increase you get. So if you're looking at just like bit output from the industry, like they will get more bits in the same wafers if they go to QLC, and they will be at a lower cost. Like, this is just fundamental. And this is the whole reason why you want to go to QLC. Now, at this cost reduction is a trade-off. The trade-off is endurance, retention, and write performance. If you're storing more bits per cell, you have more voltage levels, and you have to do different programming stuff. And the way that this works is it takes more power to do the NAND programming. And so typically there's a lot of trade-offs on like the write performance. Now, some of this is alleviated when you go to these like a lot higher capacities. You can at least get reasonable write performance, at 25 watts. But just remember, this is a massive trade-off, right? So you're going typically from like a 10,000 cycle program array cycles for enterprise TLC. QLC ranges from 1,500 cycles at some of the main vendors. I think Solidigm has 3,000 cycles for their like hard drive replacement, high capacity QLC, and then they also have like a TLC replacement that is like 5,000 cycles. So what Cameron said is like it's all across the board. As far as like there are a bunch of vendor differences in the QLC, but we do see something kind of standardizing around this 2 terabit die, which enables these 60 and 120 terabyte SSDs. So it's very clear that these are very desirable for AI workloads where power is a huge constraint in the data center, or they want to alleviate network bottlenecks by just basically having a lot of capacity, local to the storage nodes. And all we can say is people are buying these really high capacity drives as fast as vendors can make them. So now it's a scramble of like, oh yeah, okay, we need to look at this high capacity QLC. There's always going to be this TCO story of like people. By the way, that's the origin of the SNIA TCO model, was like me doing a bunch of analysis on QLC versus hard drive racks and looking at some of the various workloads, and it gets really interesting, right? When you're in that like 3x to 4x dollar per gigabyte range and QLC versus hard drives, and you have like all these extra IOPS for deduplication and compression and erasure coding and stuff. Like there's all this fun stuff you can do with TCO. But yeah, just as a reminder, QLC is always a TCO thing. It always will be a TCO thing versus TLC. It is cheaper, but it has a bunch of trade-offs. And whenever you're doing trade-offs, it's now a TCO discussion.
And one thing that you brought up, and it's starting to then move to the fore, that when we talk about like life cycle, it means from manufacturing, pre-manufacturing, like we're talking about the artifacts that are generating the physical, drives and memory themselves, and then all the way through to destruction. So it's beautiful to see more and more discussions. We talk about life cycle, meaning quite literally birth to destruction at the physical layer. And we're seeing more I'll say a lot of centralized use. Before, it used to be every enterprise would have bought up all the NVIDIA, gear. And now it's obviously the hyperscalers that are doing a bulk of the buying. And in doing so, that means that we could probably get more efficient use of it, because they're, by the nature of their sales cycle, they have to make it effective and efficient for them as a business. So I hope that in doing so, while centralization, decentralization, there's a continuous battle over who should own innovation. But it's like, we're going to be able to do stuff, innovation at scale, in some of these pieces of hardware that we couldn't have had access to unless it was in that sort of shared model. But anyways, that's just my piece as the outsider looking in of, I'm excited by what we've got coming ahead, and that we're not just talking about speeds and feeds, and TCO is far more than just what it costs me to buy the drive.
Mm-hmm.
Now, power efficiency, again, close to my heart. I'm somebody who, I do have a number of children who I want to have a number of children, and I hope that they have plenty of excitements in the outside world to enjoy, and that is from things like better things what we're doing around power efficiency. We're changing the way we do computing in general. So when it comes to power efficiency, down to the metal, what's new, and what should we be really looking forward to in 25?
I gave a presentation at FMS this year on power efficiency and SSD controllers, and where we started was in consumer SSDs, the drive sits there 99% of the time idle. So power efficiency in a laptop is all about battery life, all about how fast can the drive go to sleep, go to zero power, and then how fast can it wake up. And these are all about these NVMe power states and PCIe L1.2, very low power states. And so none of that works in the data center because you have very tight latency requirements. You can't even but by the way, consumer drives are really good now. They can go to zero idle power and get back in 5 to 10 milliseconds, which is like the latency of a hard drive. That's pretty amazing.
It's pretty wild.
But still too much, right? In the data center world, we're talking about 50 to 100 microsecond read latency, like 5 milliseconds, way too much. Those don't work. And obviously, you have you have battery backup, and you have power loss capacitors, and you have PLI stuff. So some of these tricks to go to sleep don't exactly work. But the important part is in computing SSDs. Historically, the conversation is the assumption is these things are always being used, and the measure of power efficiency is performance per watt in the active state. So you run an active workload, and you measure how much active power it's consuming to run that workload, and then you divide the performance by the amount of power in watts, and now you have performance per watt. This is a really important metric for a ton of reasons. So one, we just talked about these form factor power limits, which is okay, if you were at an interface limit or a form factor limit of 25 watts, the better power efficiency you have, the higher performance you can deliver at a certain TDP. The example I gave was actually going the other way, which is saying, okay, well, we have a 25 watt drive. What happens if we cap the power at 16 watts? Okay, well, you want to know what your performance per watt is, so that if you have a better performance per watt, then you won't lose as much performance when you're reducing the power outflow. The power savings aren't just on the drive. I think people forget that the drives go into a system, and then the systems have fans and all this other stuff going on. And when you have a drive that consumes 16 watts instead of 25 watts, and by the way, hyperscalers have been playing this TCO game for a long, long time, running drives kind of close to their operating temperature towards the upper limit to make sure they run fan speeds as low as they absolutely can to basically reduce the power on the servers and reduce the TCO. So there's the whole sustainability angle, which we haven't even discussed yet, but there's all the what I just mentioned is the practical SSD architecture applications of performance per watt, which is understanding how much power can you deliver in a certain power envelope, in certain form factors, modulating at different power limits for certain customer requirements and certain use cases. The other benefit is that if you can, lower the active power in the use phase and lower the TCO of the server, you have less wasted power on idle power, on thermal loss and fans. And there's a bunch of work going on in the sustainability space to enhance the PUE metrics to be able to describe how do you actually measure that inefficiency at the server level, not just at the data center level. Traditionally, they've been talking about PUE at the data center level, like the cooling and at the data center level, at the rack level. But there's cooling within a server, right? It has fans, and you need to be able to quantify that as well.
Yeah, I mean that's also where EDSFF comes in with the cases and the heat sink, so you can run the fans at lower CFM and help keep the power consumption down. Taking that metric IOPS per watt or performance per watt that Jonmichael was talking about. I mean, you can factor in a cost, so you can look at IOPS per watt per dollar, kind of extend that to really take a look at the economics. In addition to the performance, and as far as power efficiency goes, the power consumption of a high cap drive is also still going to be it's not double the power if you double the capacity or triple the capacity. You still need to keep either a 25 or some sort of constrained power envelope. So, I mean, that's where additional efficiencies through QLC and eventually 5 bits per cell come into play.
And I kind of touched on it briefly, but I mentioned when a workload has a drive that's idle for an extended period of time, now you need to optimize idle power. And we started to see that. I think Micron was the first to announce a drive that actually has a decent power reduction for L1, in a data center drive. I think the new high cap drive goes to like 5 point something watts to 4 watts in a L1 substate, which is great. Like, it doesn't sound like a lot. It doesn't sound like a lot of savings, like a watt and a half or something, but that's a 20 to 30% reduction, right? It's actually a pretty big chunk. And so now in this world where you're replacing potentially hard drives with a QLC or high bits per cell or something, and you have a drive that can do hundreds of thousands of IOPS, but you have a hard drive workload that's 200 IOPS, the drive's going to be idle a lot of the time. So now you have to figure out, like, how do we save the power on the drive side? And so we're not there yet from the data center side as far as like those technologies being deployed, but we have hyperscalers like actively asking those questions, which is great, because I was asking them like 4 or 5 years ago in OCP, and everybody was like, "Shut up." Like,
yeah, that's right. Yeah,
what are you talking about? Like, we never are ever going to use L1 substates in a data center drive. Like, just don't even talk about it. So.
Yeah, when it's funny, because that becomes this thing that we find, like, there's an innovation that will create an efficiency in something that we thought was a dead technology, and then that ultimately becomes the new technology. It's funny. I'm on the straight software side. I'm a Ruby on Rails fan just because it's super easy. I've been using it for so long, and it comes out of the box with SQLite. And the first thing you do is get rid of SQLite, because, dear goodness, why would you ever want to use that anywhere but on a tiny machine? Well, now, because of innovations that have happened at the hardware layer that have helped the OS layer, then they've made adjustments in SQLite that make it as performant, if not more so, and as scalable as most Postgres implementations for moderate and to large size sites. So we're seeing software development that's being enabled by work that's happening closer to the metal. And so the real, like, the impact is so broad, and that's what's exciting to me. I'm just like, because it's not just this one thing that we're innovating on, it's the entire ecosystem that sits atop of it. And I know every day is a bloody wondrous day to be in computing. I don't know. I'm excited to talk about it every day, but maybe I'm too much of a nerd. I don't know.
I think we all are at some level.
That's it. Well, and high cap drives. Let me tell you, I was on a previous podcast. I was talking about, remember the days of the excitement when you could get, we've got 64 gig drives. What? Oh my goodness, this is wild. This is an unlimited amount of storage, then 128, then 256. And now, like, you wouldn't even hand someone a free, USB stick if it was less than 512. You're like,
what am I going to do with that?
Yeah, exactly. What are we going to do? Keep one picture on it? So let's talk about what's the future of high cap, and where are we seeing high capacity work show up, in that enterprise type of display.
Well, I mean, the most talked about place right now is AI, and AI certainly has a demand for more storage. But I mean, for many years, 960 gig and 3.84 terabytes were the sweet spots. And then things, over the years, even not that long ago, they quietly went up to 8 terabytes and 15. And And I know that my company was one of the first ones to offer a 30 terabyte SSD. But those were kind of used in, kind of special use cases. Then once AI became a reality, 30 terabyte is kind of like the starting point for high cap drives. And this is also where, talking about EDSFF, where 2T and E3.L and maybe 2T, this is where the high cap drives are going to kind of be most prevalent. This is definitely high. AI has spurred on the high cap race, and it is every company is sprinting in it right now.
So I
was going to say, it's kind of like when we look and we say, why do we choose these sort of moonshot missions, and what does it actually get us? But like, while AI doesn't necessarily seem like it's doing what we would hope or expect it to do at the moment, what it is doing is creating a fantastic, burgeoning innovation around the data center architectures and hardware and software to allow AI to be efficient and performant. So while we're sitting here getting it to generate emails for us while burning off thousands of watts, at least we can hopefully get it better down to the bits and get these drives where they're getting the most out of that hardware.
Yes.
And sorry, Jim, I cut you off there.
You're good. You touched on one of the use cases, which is terabytes per watt, right? And if you have a 122 terabyte drive, and the NANDs, the vendors have all said, yeah, we're going to go to 1,000 layers or whatever, right? So it's not going to slow down, right? Certainly, paths to 256 terabyte drives and above, and even though hard drives, Seagate's shipping HAMR in production, and they just announced 30 terabyte CMR and 32 terabyte SMR in in production, even for the channel. So that's, the trend is going up on hard drives, but SSDs are they're already 4 times bigger, and they're a lot, half the physical size and fraction of the size. So from just a capacity standpoint, SSDs are already far ahead, and that's going to be continually stressed in data centers where they have no more power. And this could be in a regional data center, in a colo, or AI data center where they're like, okay, well, we didn't, yes, they cost a lot more. SSDs are still 10x the price of hard drives, but maybe if the QLC market comes back down to the earth, maybe it's going to be like a 6x. And now, okay, if you have a 6x multiplier on the price, but you can go from 5 racks of hard drives to 1 rack of SSDs with the same power, like, man, these are really tough decisions for data center operators to make. Remember, you also don't just get the capacity, you also get a ton of performance. Now you can open up a bunch of like AI use cases for reading that data. So some interesting thing we've seen. Well, I think one thing that we mentioned on QLC is just like a obvious, it's from a technical standpoint, it's actually physically cheaper. There's more bits per cell. But the other trend we've seen is some of these vendors have used like consumer TLC, to basically get to market faster on a high capacity drive, like with 16 die stacks, or even potentially these like crazy 32 die stacks of consumer, 3,000 program array cycle TLC NAND. So there isn't just one way to build a super high cap drive, but certainly QLC is the way to build the biggest drives right now. And as far as the use cases, I don't think, like there are tons of use cases for high capacity SSDs, object store, power savings in this training data. All the training data is going multimodal. I just got the update pushed on my Tesla this morning, which I'm excited for the new self-driving that they trained in the new X.AI data center with all these petabytes of footage from high bandwidth, high resolution footage from the new cameras. And it's so awesome, right? That these new training sets, these new big data, you want fast SSDs to basically kind of do that type of workload. So I don't think it's going to slow down. I think the demand, we're already at like 20% of the bits shipped at QLC. I think it's going to continue to ramp. And now all the analysts are finally like, yep, now it's time. QLC is going to go nuts next year. So
it's such an interesting innovation area because, I think of like general optimizations, we always link back to the sort of gold rat-esque type of things of, find the constraint, sublimate the constraints, and we look at this in like, how do we just tackle just the bottleneck? But what's actually happening with these types of innovations is that we're eliminating someone else's bottleneck by adding innovation in an entirely different area. So that's why there's so many moving parts, but we're seeing them all converge together. That allows, like you said, stuff that's going on in the XAI, data center that just would not have been possible 5 years ago from 50 different areas of innovation. And then now that we're actually pushing the technology with stuff like FSD, oh, I love it. I love seeing use cases that are real, not just like, what could we do with this? You're like, we're already doing it. It's being used every bloody day.
Now, I forgot the actual plug for the SNIA SSD SIG. So if you are working on SSDs and big SSDs, come to the SNIA SSD SIG. We have, I believe, Solid IM is about to contribute a paper on, how to benchmark, large capacity drives for things like endurance, like something, if you have like an indirection unit size that's not 4 kilobytes, maybe much bigger, so you can reduce the amount of RAM, the typical JEDEC workloads just don't make sense. So there's a lot of nuance of how do you test these big drives. And that's actually a lot of the technical discussion that we're driving through the work groups.
Yeah, instead of even as a buyer of just, enterprise storage gear for SANs, and you'd get those performance numbers from the vendor and you're like, you sure these aren't just linear 4K reads? I'm like, I think that your iometer test is cute, but let me try it out in production. And every time I put it in production, I would get told about a month later, well, you see, the problem is your workloads. I'm like, oh, it's my fault. Sorry for me and my silly workload getting in the way of your performance. So, I could literally go on for hours on this stuff. You guys are both fantastic. And so thank you both for sharing what's coming up. But quick closer, what's super exciting to you, and how do we best get a hold of you if you want to chat more on this stuff? Let's start with you, JM, and then we'll close out with Cam.
I mentioned, Cameron and I, the SNIA, if you're a member of SNIA, you should come to the SSD SIG. Everybody's welcome now. I think the 2025 rules are different where, you used to be part of CMSI or whatever. So they're anyways.
Yeah, it's open to any member now.
It's open to anybody next year, and so just come into the work group, and if you want to talk about SSDs. The TCO stuff. There's a ton of interest in AI TCO, and like I mentioned, now you're talking about IOPS per dollar and stuff. Like before, it was just gigabytes per dollar. So now I'm going to be updating all the SNIA TCO models to basically be ready for AI workloads, and that's going to be a lot of fun. I can't wait. NVIDIA is asking me to do this, and it's going to be fun.
Fantastic. Cameron?
Real quick, you can connect with me on LinkedIn or cameron.brett@qlc.com if you want to email me directly. Again, I think one of the big focuses that we're doing in the SSD SIG is, looking at SSDs for AI, as well as kind of continually monitoring and kind of being the advocate for EDSFF, this form factor transition away from 2.5 and M.2. So I think that's some of the exciting stuff that we have going on in the SSD SIG.
And as they say in sports, you got to be in it to win it. And getting joined up with SNIA is super easy. The new membership options, we had a great discussion with Jay Metz talking about how the membership look for 2025. So it's much easier to get involved. It's much easier to get involved in multiple disciplines within the group now. So every barrier to entry is being lowered, and just the fact that you can sit with a peer group who is living these problems. If all the stuff, if you're sitting in your chair and you're shaking with excitement like I am, and you want to go and start putting the stuff into action, then get beside JM and Cameron and all the fine folks at SNIA. There literally is no better community of people that are really doing fantastic things, and there's lots of opportunity ahead. So let's see what's coming up with 2025. Thank you both for having, number one, created great content together in 2024. It's been great to spend time with both of you. And for folks that want to get involved, again, head to SNIA.org, check out the other podcast episodes as well. We're both on audio, and we have these on YouTube. So if you'd like to see these beautiful smiling faces do more, oh, right. And of course, JM, you mentioned stuff that's from SDC and even some of the other stuff with OCP. There's tons of great public-facing content. So even if you missed it, you didn't necessarily need to be there. Check out the YouTube channels. There's lots of great content available for recap and review. And I'm a fan. So with that, both of you, thank you very much. And for all the folks that are watching and or listening, thank you. And Happy New Year. And we'll see y'all in 2025 for the SNIA Experts on Data crew.
Yeah. Thanks, Eric.